Thank you. Thanks for the intro, and thanks for having me. So what we're going to be talking about is how we can scale end-user programming. End-user programming today is largely an individual activity where the end user sits at his laptop, play around with some model, execute on a fairly limited data size, and then uses the resulting model by himself. And we want to scale that up so that a group of end users can collaborate on a model together as you would on a software project. And that model can be sophisticated and run over large data sets. And that final result, that model can be distributed to other users who may find it useful as you would a real piece of software. So those are the scaling challenges in end-user programming. Before we get into the details of that, I want to just set the context for the size of the problem we're interested in. At LogicBlox, the kind of user that we're interested in are the enterprise users, users who use business software to solve problems at work. And globally, we're spending $150 billion on enterprise software this year. That's according to Gartner, which is a leading analyst firm. This number is expected to grow to $201 billion. To just put these numbers in context, the global consumer software market is only about $94 billion. So the enterprise market is over 50% larger. The United States Federal Student Loan Program, the Pell Grants, is only $35 billion. NSF, where some of you might get your research funding, is $7 billion yearly, and DARPA is only about $2 billion. And this is all to say the enterprise software market is huge, though you may not be very familiar with it.
Are you saying we can get funding?
You might.
Can we get a piece?
If you work on the right problems, absolutely. Something that's really interesting about this market is that whereas in consumer software market, the same piece of software tend to be sold over and over again to millions of users, there's a lot of customization going on in the enterprise market. 75% of the $150 billion is spent on custom-build projects where a group of professional developers get hired to just build software for a company, or sometimes a department. Why is there so much customization? Well, if you look at enterprise software, they all roughly do the same kind of things. They all support some kind of bookkeeping. For retailers, that would be the buying and selling of your goods or the purchasing of your inventory. For financial services companies, that would be the buying and selling of stock and mutual funds and other financial products. And for consulting companies, that would be the buying and selling of your people's time in terms of billable hours. So everybody wants to bookkeep. And then they want to do some analysis on the historical performance. How did I do last year? How much revenue did I have? What was my cost? And therefore, what's my margin and what's my overall profit? And then they want to plan out for the future. They want to set some goals for the next quarter or the next year and play with different parameters to see how they can improve their revenue and lower their cost and make more money in general. The thing that's interesting, though, is that every company, even though they do the same categories of things, they do these things just a little bit differently from each other. And in fact, the differences in these business processes can be their differentiator from their competitors and how they make more money. And that's why they spend a lot of money customizing a piece of software just to tailor very well to their specific business process. Given that this year, globally, we're spending $112 billion building software, what kind of return on this investment are these companies getting? It's not that great, right? 68% of these projects result in marginal delivery or failure, where marginal delivery means you, quote unquote, deliver the piece of software, but it never gets rolled out to the users. 24% achieve less than 50% of the expected benefits. Only 8% of these projects result in greater than half of the expected benefits. This kind of statistics is exactly what's driving the end users, the users who these softwares is supposedly built for, to help themselves with end user programming tools. Excel, I'm sure you're familiar with, the stalwart in this area, huge installed user base. There are some newcomers in this area. Tableau and Qlik are two of the biggest players in this new category of software called self-service business intelligence, where self-service is a new word for end-user programming. And the last quarter, they released revenue for very healthy growth and very good revenue, right? So this is a growth area. These are very effective tools until the problem you're trying to solve with them reach a certain scale. What does that mean? well, your problem could scale beyond the expressivity that the programming model in these tools support, right? These tools typically are very good at supporting bookkeeping and historical analysis. However, they tend to fall apart a little bit when you want to do some sort of forward planning with them. And recall, that's one of the 3 major activities that the enterprise does. Your problem could also scale beyond the data size that they handle. Typical enterprise would have probably on the order of hundreds of gigabytes, if not terabytes of data. Petabytes is fairly uncommon, right? There's only so many Googles and Facebooks. These tools that we're just looking at, Excel and Tableau, et cetera, they support on the order of 2 to 4 gigabytes of data. Now, of course, you can use the option to live connect to a database, at which point you scale to whatever the database supports. But at that point, IT has to get involved, and that's no longer an end user project. It becomes a custom development project. You may also want to scale beyond just a single user. You want to share your model, and you want to have people collaborate and use it together. Concurrent read support is easy. It's easy to scale to a lot of concurrent readers. Concurrent writers, though, is very challenging, especially when you combine it with large data size and sophisticated model. So Excel, for example, you can, of course, go to Office 365 and get concurrent writers on your Excel spreadsheet. But then you are limiting your workbook size to 256 megabytes, right? So it's this balance between sophistication of model, concurrent writers, and data size that's challenging. And finally, you might want to scale your, the program that you wrote to beyond just yourself. You want to distribute it to others, or you want to scale it so that others can collaborate with you on the model. So the versioning and the sharing support in the existing tools leave something to be desired. It's typically not supported very well. So these are the challenges that we're tackling at LogicBlox. And in fact, they're well-recognized challenges that these existing players are tackling as well. But for today's talk, we're going to look at what we're doing at LogicBlox. In terms of supporting more sophisticated programming model, we provide a relational programming model that uses parametric relations with bidirectional and probabilistic rules, and both of these are very important properties when you want to plan for the future. And a declarative visualization language for users to lay out their UI, okay? For the execution engine, how do we actually scale the evaluation of a very sophisticated model to large data size and be able to support concurrent writers? Well, we realized very early on that our language runtime had to be a scalable database as well if we wanted to evaluate these models on real data size. And that database has to be able to handle the wide range of workloads that we have to support bookkeeping, historical analysis, and forward-looking planning. It has to have asset transactions because we want concurrent writers. And if you don't have concurrent writers, then the user might experience extremely odd behavior when you don't have asset. And of course, since we're targeting end users, we want to make sure that the engine can perform well without a lot of manual tuning. Performance tuning is just not something that end users are typically very excited to do. And finally, to support the scaling of the deployment, we wanted to have built-in support for versioning and the sharing of both the model, which is code, and data. All right? So this is what I'm going to cover today. Obviously, in the next 25 minutes, I can't cover all of it. So what I'm going to focus on is a modeling part. We're going to look at our programming model. How do we keep the abstraction level high, but at the same time give users a lot of expressivity for what they need to do? And then we're going to look at how we support versioning and the sharing of model and data. All right? The way we're going to do it is by example. We're going to look at the implementation for I don't know why it doesn't want to stay on that slide. There it is. An example application that we built in LogicBlox, and let me just give you a quick demo of that. OK, so this application, I call it Minty. Is everyone familiar with mint.com? OK, OK. There's somebody in the back shaking their head. it's something for you to keep track of your financial transactions and then do some analysis over time and set budgets, etc. What we build is 2 very simple pages. The first page just help you keep track of your transactions. You have your date, amount, type, the merchant and the category, and I can do some data entry, and that's what bookkeeping is all about. I think today is 10/29, 2015. I spent $455. Let's say that's an expense, and it was at Starbucks, right? I can do this sort of thing. And then we also have a second page, which is used for both historical analysis as well as for planning. So here I'm looking at my historical spending versus income. I also have some computed values like net income and the percentage of my income that I spent, right? I can look at, I only have 2 years worth of data, so we can look at 2014 and 2015. A very common activity that users want to do in planning, and I'm going to explain this, is they don't just want to go and adjust their income and expense. When they set a goal for, let's say, this year, they actually want to say, well, it doesn't matter what my income or expense is, I just want to make sure that I spent no more than 70% of my income. So I'm editing the percentage here. And as you can see, as I edit that, all these values change to adjust so that my expense percent becomes what I entered. And this is exactly where bidirectional computing comes in. And it's a very common use case that you want to do this in enterprise planning. Okay? Something else you might want to do is, let's say, I do want to go and edit my expense, but what I want to do is I know that I want to spend, let's say, $70K this year. However, I also know that for December, it's Christmas, and I'm gonna, have to budget $10K for that. Now, when I commit this, say calculate, this is another form of that bidirectional programming where my 70 at the year level is held, my 10K at the month level is held, and they kind of spread around the rest of my months to help me budget out the rest of my month. Okay, so that's a second form of bidirectional programming. So we'll be focusing on both of those today. I'm not really going to have time to talk about the probabilistic part, so that's going to have to be another time. All right, let's start with the data model. Everything in LogicBlox is a relation. In fact, everything is a parametric relation, but I'm going to need to explain a couple things before we get to that. For this first view here, we have this table effectively, and we model them as 5 relations where I have date, and date has a label that's shown here, and it has a key type, which is transaction. That's a user-defined type. You can think about a user-defined type as effectively a single column relation. Okay? And I have a value type day, which is built in, and I have amount. That's also transaction, and the value type is decimal, which is also built in. And then I have things like transaction type and merchant and category. So 2 things to notice here. One is that every relation we have is in 6th normal form. I don't know if the audience is familiar with what that means. It means that in any given relation, there is no join dependency. But if that doesn't make sense, I think a fine working definition for this talk is that our relations are key value, very narrow relations, right? The key doesn't have to be just a single key. You can actually have multiple keys, but it's the set of keys to a value, whereas in a traditional SQL database, you will probably define this table as a wide 6-column table. In our data model, you define it as a very narrow 6th normal form. All right? The second thing to notice here is that our value type can be either discrete or continuous. So decimal is continuous, whereas merchant is a discrete value type. There's only a fixed number of merchants, and there is no merchant that lies 0.895 of the way between Amazon and Whole Foods. Okay? So this is a discrete value. Putting the 6th normal form and relations with discrete value types together is what brings us to parametric relations. What do we mean? Amount that I declared here is not just one relation. It's actually a whole family of relations. This definition gives me the base relation, which is amount parameterized with a key type transaction. However, since I know that I can also relate transaction to merchant using the merchant relation, I can compute from that amount parameterized by the key type merchant. And let's just see how we compute that. We start with the amount tuple at transaction, parameterized by transaction. I have 3 transactions here, each with the amount 5. We also have the merchant tuples parameterized at transaction, where transaction 1 and 2 both went to merchant 1, and transaction 3 went to merchant 2. From this, I can compute amount parameterized by merchant. And now merchant 1 has the amount $10, and merchant 2 has the amount $5. Effectively, I'm doing an aggregation here. Okay? And the aggregation method I'm using is total. The user can actually parameterize that and say, rather than total, I want to use average or min and max. But total is the common one. Since we also have a relation that is category parameterized by merchant, then I can use these two together to compute amount at category. We also have a all member that all discrete members implicitly map to, and from that, I can derive the amount at all relation, which is a single column relation that just contains one amount. That's the aggregation over all the amounts that I have in my workspace or my database. I can use the day relation to compute more. I can aggregate amount at day, and that goes up to month and year and all, and that's being used in computing our income and expense at month, for example. The parameterized relations also don't have to have the same number of keys, right? So I can compute using amount parameterized by transaction and merchant at transaction and day at transaction to derive amount at day and merchant. And what that tuple looks like, or what that relation looks like, is this. I have these 2 key single value tuples where it says for a given day, for a given merchant, how much money did I spend? Yeah? And as you can imagine, I can go up from there. I can compute amount at month merchant, amount at month category, et cetera, et cetera. It's probably obvious by now that there's actually an infinite number of parametric relations we can have from just a single definition, right? And the fact that we can automatically compute these for you or for the users by them parameterizing the relation differently is very useful in them concisely describing what kind of analysis they want to do at the different levels. And it's also very useful in defining rules, which we're going to look at next. The relations that we have defined so far are relations that we expect users to put data into. We can also have rule computed relations, and there are 4 of them in our example application. Income is amount, where type is income. Expense is amount, where type is expense. Net income is income minus expense, and expense percent is expense divided by income. These relations are also parametric. So what that means is my expense percent, I can parameterize it with these different discrete levels that I have. So what is the expense percent at the year level then, which is something that we looked at on our second page, right, of our example application? Well, based on what I've just told you so far, you might say, oh yeah, then you just map it up from expense percent at month. But this will be wrong, because expense is a percentage, right? I can't add up all my expense percents for all the month, and that's going to add up to 100% for the year, which is obviously not what I want. So for the rule-defined relations, what you do is you push the parameterization actually inside of the formulas, right? So in this case, it's fairly obvious how we would do that. It's not always obvious like this, but I'm going to leave that topic for a different talk. The key thing to take away is we have 2 different ways of computing parameterized relations, by kind of directly aggregating up or by pushing it across to rules for the rule-defined relations. Those are what you need to know for our parametric relations. Now we can take a look at the bidirectional rules. All right. So bidirectional computation, as I showed you in our little demo, is very useful when users want to actually edit the computed values. Okay? So this set of rules says net income is a computed value. It's computed by income minus expense. But I'm going to give you 2 ways to inverse that computation. One is expense is equal to income minus net income, and the other one is income is equal to net income plus expense. You might say, well, these are kind of obvious. Why do you even need the users to write them? It is true, we actually do generate these when it's possible, but there are cases where it's not obvious what the inverse is. For example, it's often that user want to invert a running total, yeah? And there are actually many valid ways to invert running total, and we need the users to tell us which one they want, and different businesses do it differently. All right, so that's our rules, and now what we do is every time a edit is made to a computed relation, we need to find a valid update path back to a source relation. So in this case, our net income is our sink relation, and income and expense are a source relation. We've drawn a dependency graph here. The solid line here indicates a forward computation, and we have two dotted set of paths for our backward computation. I1 indicates the expense rule, I2 indicates the income rule, where I1 is preferred. This is basically, the order of these rules is the user's way of telling us, use the expense update if you can. Otherwise, do the income update. So let's see when we can actually, we have to use one versus the other. Well, if we just edit net income, then both of these paths are valid, right? Because neither of them will go and try to edit the value that I already edited. So let's just pick I1. That's fine. However, what if the user edited both net income and expense? I can no longer use the forward path, of course, nor can I use this I1 path because it's trying to compute the value that I already edited. So the only valid path left is I2. And that's one I pick. The search for update path is not local to the rules. It's actually global across all rules. So here we have our expense percent rule, which also has an inverse that says expense equal to income multiplied by expense percent. And this is a dependency graph for both rules. What happens when we edit both net income and expense percent? Well, let's get rid of the two forward paths that are no longer valid. Let's say we pick I1 because we see that that's preferred by the users, and we get rid of the other paths that are invalid. Now we have no way to actually propagate the change of expense percent back to any source relation. And this is when we need to backtrack to say, okay, I1 was a bad choice. Let's pick I2, get rid of the invalid path, which is there's no invalid path at this point. And now we can pick I3, and we're done, right? So there has to be some sort of backtracking. The good thing is that typically there's not a lot of rules in the mutually dependent group, so there's not a whole lot of backtracking going on. All right, I glossed over some details here. When we said that, we found our update path, and that's great. The updates can be propagated back to these sink relations using these inverse rules. Of course, income is not just one relation, right? Income is a set of relations that can all be parameterized at different values. So when we're making an edit, we're really making an edit at one of the parameterized version of income. So if we did that, then how do we actually propagate that change back down? This is the second form of inverse computation that I demoed. When I modify income at year, how does that get changed back down to month and date and finally transaction? So as you recall, these different parameterized versions of income are computed from other parameterized versions. There's also an implicit inverse computation path between all of these relations. And the way you do it is through what we call parametric spreading. So there's different spreading policies that you can use to invert an aggregation. A very common one is by ratio. If I double the income, then I double for the year, then I double all the income at the month level. Right? Something that is a little bit tricky, though, is what happens when the user modify income at year and income at month at the same time. Right? As I demoed, I can modify my income for 2015, and I go and edit my income for December because I know I'm going to be getting a bonus, and that's part of my planning. And now the parametric spreading actually has to spread around the changes to both of these relations. Yeah? And so that's, I'm not going to have time to get into the details, but that's part of the complexity of supporting parametric spreading. So that's it. We've gone through the model part and we've gone through the rule part, and now we can look at how we actually put up the two UIs that we saw. So our work in this area draw on a lot of great research that's done in the InfoVis research area. A lot of this came out of the Stanford Visualization Lab, led by Pat Harahan, your Oscar winner, and his students at the Interactive Data Lab at University of Washington. Some of this work has been commercialized. VisQL has been commercialized into Tableau. We use this open version tool, Vega, here. All right. So the fundamental concept you need to understand about our visualization language is every tuple in our relations is a point in a multidimensional space. So for instance, the amount at transaction relation, every tuple in there is a point in this two-dimensional space where on the x-axis I have transaction, and on the y-axis I have decimal numbers, right? So if you see a point here, that means I have a tuple for transaction 59 for the amount 120-ish. Similarly, for discrete valued relations, there are also points on a multidimensional space. This is merchant at transaction. So if I have a dot here, that means I have a tuple for transaction 12, merchant Amazon in that relation. There are also some meta relations of relations that are important in visualization. So I can have a set of relation names that effectively is a single column relation that contains all the relation names in my application, right? And I can lay it out on the x-axis here, amount, expense, income, net income, expense percent, for example. And I can lay out transaction on the y-axis, and everywhere you see a dot here, that means that in my meta relations, there is a tuple for the amount relation for transaction 1. And here, since a transaction cannot be both expense and income, you can see that there is an expense tuple, but not an income tuple. And you can see that for month, for example, we have tuples for all relations and all months, okay? Because there's not a single month where we didn't have any transactions. Now we've learned enough to see how we can actually declare this table. Declaring a table or a chart in our system is effectively laying out the measures and the different relations onto a two-dimensional axis, or two-dimensional space. So here I'm saying on the x-axis, put all the relation names on there. And I can restrict the relation names that's used so that I don't display every relation in my system. I have date, amount, type, and merchant. On the y-axis, put the transaction. Okay? And I get a table like this where wherever there's a dot, that means there is a tuple for date for transaction 1, amount transaction 1, etc. So a dot is, of course, not very useful. What do we actually put here? Well, the very basic thing you can put there is a textual representation of the value of that tuple. That's where this mark comes in. I say the mark I want for the amount data is text. And I'll just put all the text here. And if I use the mark text for all the relations, then I effectively get a table. So this is how you lay out a table, a grid, in our system. In addition to text, though, you can also say, well, I want the type to be color. Now I'm mapping all the values of amount to some color spectrum. In this case, we're defaulting to some varying shades of green. But of course, I could have said the color spectrum I want to use is from a deep red to a dark red to indicate the expenses versus income. Okay? And this effectively gives you a heat map. Now, how do we actually define charts? It's the same thing. Here on the x-axis, I put all the month on the x-axis. And I'm saying on the y-axis, put the meta relation values with a type continuous. And the relations that I want to plot are income, expense, and net income. And for the income one, use the type rect, which gives me bar charts. But for net income, give me line. And that gives me a line chart. Okay? There's a lot more detail that I'm not going to have time to go into, but this is the basic idea behind our declarative visualization language. So by now, you've seen the entire implementation of our two-page application. Our model consists of relation definitions and a set of rules that are bidirectional. And then we had 3 pieces of specification for the 2 tables we have and the 1 chart, and that's all. Now let's take a look at our evaluation engine and how we actually evaluate these models. Because of the kind of end-user programming that we knew we wanted to support, it placed a number of requirements on the evaluation engine that we had to have. They roughly fall into 3 categories. Of course, we want to scale, but we also wanted to minimize incidental complexity in the models because we're looking at end users. And we do want to support a live and collaborative development environment. So since we wanted to scale to enterprise data size, we're looking at, certainly on the order of terabytes of data. We knew that we had to have a database. And because we also wanted to scale to concurrent writers, we had to build a real database with ACID transactions. Okay? But of course, this is also a language runtime because we didn't want to we wanted to minimize the integration between database and language runtime. We didn't want the end user to sit there and figure out, well, do I want to use a framework like Hibernate or Django, or do I want to directly talk to the database protocol? So that question is just moot in our system because your database is your language runtime. We want to minimize the integration between multiple databases. Typically in enterprise software, because of the range of transactions or the range of queries you want to process, the bookkeeping, the analysis, and the forward-looking, you typically have multiple different databases. And we didn't think that end user could really handle the integration between these different databases. That's typically the hardest part about the project. So we built a database that's hybrid, transactional, and analytical, so that there is a single database and language runtime for the models that the end users built. And we wanted to minimize the performance optimizations. We didn't think that end users should have to worry about, should I create an index to make my model run fast, or should I use stored procedures versus queries? So we built our database with a novel join algorithm, with a really smart query optimizer, and it distributes work across multiple cores when that's available. By the way, our runtime is by far the most written about part of our product, so I'll give you links to the various publications about the join and the query optimizer, et cetera. Okay? And finally, we knew that we wanted to support live and collaborative development because that's important for end users. So the underlying engine has to be responsive to changes in the data model, in the logic, and in the data. So our evaluation engine has an incremental compiler, and it also re-evaluates incrementally on program and data change. And finally, we wanted to be able to support the versioning of your schema and your logic and your data because we wanted to support end users as if we support real developers where they can actually have checkpoints of their program and their data. So we built a fully versioned database, and this is the part I'm going to get into a little bit more next to look at how we actually use the fully versioned database. Okay, so what can our fully versioned database give you? Let's say we start with our initial state of the database, minty at v0. Every state change I make to the database, every transaction that actually writes something and changes something, automatically you get a new version of that database. And you can always refer back to that version and inspect the state of your world at that point. You can also branch from any point. And the branching is instantaneous. So I can branch off minty v1.1, minty v2.1, and then I can keep going on that branch and then further branch off from that. What this allows is for the end users to actually create their own checked out version of the application. And this is actually, it sounds kind of crazy that an end user might want to do this, but this is a very common scenario in our enterprise usage. Usually what people want to do is they have a model that they got from somebody else, and they say, I want to go and work in my own world a little bit, manipulate the formula a little bit, manipulate the data a little bit, and when I'm ready and good, then I want to check it back in. But when I'm not, I really don't want anybody to see my work yet. Very much the way we would work, right? In addition to this, your logic can actually, the rules you write can actually refer to the same named relation at different versions. So I can write one rule that compare net income at V1 with net income at V2, and I can say, okay, what are the tuples that are in both versions? What are the tuples that's in one version and not the other? And what this also allows us to do then is to be able to write merge rules. Yeah, in our implementation of the merging support, then we can just write logical rules that implement various kind of merging policies. Or for the extremely motivated end user, they can write their own merging policies if they wanted to. And of course, we can instantly revert to any version, as I was saying. What this gives us is we have autosave, basically, at every point of a user's work, and then they can revert back to any version that they want. And of course, the reason we can do this is because our database and language runtime uses persistent data structures all the way through under the hood. Yeah? So these are the pointers to the publications we've had. Live programming in LogicBlox system. This discusses our compiler, which uses logical. Yeah?
So you're talking about versioning of data? How about versioning of code?
It's both. It's versioning of the data and schema. So let's say I branch off a version, I can create a new relation there that's not visible in the version I branched off of until I merge it back.
So how about consistency?
Of
Well, data that is, well, if you merge off or if you branch off a version where you evolve your relations and your rules,
right.
And then, well, the branches may not be.
Yeah, so you might have relations that have the same name but different keys, you mean, or yeah. So that's where these merging policies come in. Like we can build, you know, a baked-in merging policy that just says, last writer wins. Always take mine over yours. But in the case of schema change, that becomes more complex. Then we have to probably ask the users. This part we haven't implemented yet, but you will probably have to ask user for input. Like, how do you want to merge this data back if the schema has changed? Yeah. Exactly. Yeah. So now, of course, you also have when the end user, let's say I'm working in version v2.1, I'm changing the schema, and I have to change my UI as well. So that's part that gets merged back, as well. So you do have to have some user input. Today it's very crude. It's just I'm just going to replace yours with mine. Yeah. Exactly. Yeah. No, and I doubt a full automation is really possible. But there are very simple rules that's actually good enough for most use cases. So we'll probably implement those first, and then give people a hook to implement their own if they wanted to. Yeah. Okay, so this first one talks about our methodological approach, our compiler that's incremental, it uses logical. And well, you can read this. I only have 5 minutes. I'll share my slides. All right, so wrapping it up, the LogicBlox approach to scaling end-user programming is we start with extending the expressiveness of the programming model without losing the high-level abstractions. So as you saw, and I think hopefully you agree, our language is fairly declarative and it's amenable to a business end user, but it has parametric relations, bidirectional and probabilistic rules. Probabilistic I didn't talk about, and a declarative visualization language. We build our own database, which is also our language runtime from scratch to support execution of a sophisticated model over large data sets. And that database also has built-in support for versioning and sharing of model and data to scale the deployment of the application. So some of you might be wondering, well, wait a minute, you're surely not telling me that you want the end user to go and write JSON, right? We're not. And of course, a very nice and interactive IDE is a very important part of this, and this is something that we're working on. Although I do have to say that the IDE itself, though there's a lot of innovation to be had, that's not been the problem in scaling end-user programming. The problem has been in the programming model and the evaluation engine. And then, you can build a nice IDE on top of it, but without the core pieces in place, you can't IDE your way out of an unscalable system, right? So you actually saw part of our IDE already. this application, this is our IDE. You just might not have realized it. This is work in progress. So for example, I can build up our first page very quickly with some, dragging and dropping. I can say, I want a transaction. Transactions have date and it has type and it's got merchant, et cetera, et cetera. But you've probably seen this sort of thing in, Excel pivot table, and Tableau allows a similar sort of thing as well. All right, and that's it. That's the end of my talk.
So we have a couple of minutes for some questions.